Look around you. It's everywhere. In the kitchen, you might find it wrapped around your food. Look up at the sky, and you'll see it soaring through the clouds as an airplane. This amazing material is aluminium. It is the most common metal in the Earth's crust, a fundamental building block of our modern world. But for most of human history, this incredible substance was completely hidden from us. It was locked away inside rocks and clays, waiting for our curiosity and ingenuity to set it free. The story of aluminium is not just about a metal, it's a story about human discovery, a journey from ancient mystery to the very fabric of our technological civilization. Long before anyone knew what aluminium was, ancient civilizations were already using its compounds. The Romans and the ancient Greeks used a substance they called alumen, which we know today as alum. This was a naturally occurring aluminium sulfate salt. They used it for a surprising number of things. It was a fantastic mordant, a chemical that helped dye stick to fabric, making their textiles vibrant and colourful. They also used its astringent properties in medicine to help stop bleeding from minor wounds. They were holding a key part of aluminium's chemical identity in their hands, yet they had no idea that a shimmering, lightweight metal was trapped inside. Imagine a Roman artisan carefully preparing a dye bath for a senator's toga. He adds a pinch of white, crystalline powder, alum, to the pot. He sees how the colour becomes brighter, more permanent, and he marvels at the magic of his craft. He does not know that he is manipulating atoms of the third most abundant element on our planet. For thousands of years, this was humanity's relationship with aluminium. It was an invisible helper, a chemical ghost present in pottery clays and medicinal potions. Its true nature a complete and total secret. Its presence was felt, but its form was entirely unknown, a cosmic riddle waiting for the right minds to come along and solve it. The story of aluminium's beginning is a perfect example of how science works. We often use things in nature without fully understanding them. We observe their effects, we learn to control them, and we incorporate them into our lives. From the pottery glazes of ancient China to the medicinal practices in ancient Egypt, aluminium compounds were a quiet but constant partner in human progress. But to truly unlock the potential hidden within these earthy materials, we needed more than just observation. We needed a new way of thinking. We needed the scientific method, the courage to ask what is this made of, and the tools to find the incredible answer. For centuries, the secret of aluminium remained locked away. The puzzle began to unravel in the age of chemistry. In the early 1800s, scientists were on a quest to discover new elements. A brilliant chemist named Humphry Davy was convinced that a hidden metal existed within alum. He tried to isolate it using the new technology of electricity, but he couldn't quite succeed. However, he was the one who gave it a name. He first called it aluminium and then later aluminum, a name that hinted at its origins in alum. He knew it was there, somewhere, waiting to be found. The chase was on, and the scientific world was buzzing with the possibility of a brand new metal. The first person to finally catch a glimpse of this elusive element was a Danish physicist named Hans Christian Ørsted. In 1825, he managed to produce a tiny, impure sample of aluminium. It wasn't much, just a small lump that looked like tin, but it was a monumental achievement. He had proven that Davy was right. The hidden metal was real. A few years later, the German chemist Friedrich Wöhler improved upon Ørsted method. He produced a small amount of pure aluminium powder. For the first time, humanity could see the true face of this element. It was silvery white and astonishingly light. But making it was incredibly difficult and expensive. Because it was so hard to produce, aluminium became one of the rarest and most valuable materials on Earth. Think about that for a moment. This metal, which we now use to wrap our sandwiches, was once more precious than gold or platinum. The Emperor of France, Napoleon III, was fascinated by it. He commissioned a set of aluminium cutlery to be used by his most honoured guests at state banquets. Everyone else, including the Emperor himself, had to make do with simple gold utensils. He even had a baby made of pure aluminium himself. This was the ultimate symbol of wealth and power in the mid-19th century. This period of extreme value shows us a powerful lesson about technology and resources. The value of a material isn't just about how rare it is in the earth, it's about how difficult it is for us to get it. Aluminium is everywhere beneath our feet, but for a time, it was harder to obtain than gold from a deep marble. The Washington Monument, a towering symbol of American pride, was completed in 1884. At its very tip, they placed a small pyramid, a capstone to crown the structure. And what was it made of? Not gold, not silver, but pure gleaming aluminium. At the time, it was the largest single piece of aluminium ever cast, a treasure sitting atop the world's tallest structure. The age of ultra-expensive aluminium was about to come to a dramatic end. The world needed a hero, or in this case, two heroes, working independently on opposite sides of the Atlantic Ocean. In America, there was a young college student named Charles Martin Hall. In France, there was a young scientist named Paul Héroult. Both were born in the same year, 1863. Both were fascinated by chemistry, and both, completely unaware of each other, were obsessed with the same problem: finding a cheap way to produce aluminium. It was a scientific race that neither man knew he was in, a cosmic coincidence that would change the world forever. Charles Hall was a student at Oberlin College in Ohio. One day, his chemistry professor remarked that any person who could invent an inexpensive process to make aluminium would become rich and a benefactor to the world. That statement lit a fire in Hall's mind. After graduating in 1885, he set up a laboratory in a woodshed behind his family home. Using homemade batteries and borrowed equipment, he began to experiment. He knew that bauxite, or aluminium oxide, had a very high melting point, making it impossible to melt with the technology of the day. Paul's brilliant idea was to dissolve the aluminium oxide in another melted mineral, cryolite. It was like dissolving sugar in hot water. On February 23, 1886, a historic moment happened in that humble woodshed. Hall passed an electric current through his molten mixture of cryolite and aluminium oxide. After a while, he poured out the liquid and let it cool. There, at the bottom of his crucible, were several small, shiny buttons of pure aluminium. He was just 22 years old. He ran out into the snow, bursting with excitement, to show his professor the fruits of his labor. He had done it. He had found the key. He had unlocked aluminium from its mineral prison using a method that was simple, effective, and, most importantly, scalable. The world was about to change. In a stunning display of scientific synchronicity, Paul Héroult in France was making the exact same discovery at almost the exact same time. Working in his father's tannery, Héroult, also just 22, developed an identical process using electrolysis to extract aluminium from aluminium oxide dissolved in molten cryolite. He filed for his patent in April 1886, just weeks after Hall had made his breakthrough. Today, this revolutionary invention is known as the Hall-Héroult process. It is a testament to the power of human ingenuity, showing how different minds, when faced with the same great challenge, can arrive at the same elegant solution. Their shared genius turned a precious metal into a material for the masses. The Hall-Héroult process was the spark, but to truly fuel the fire of mass production, another piece of the puzzle was needed. The process required a massive supply of pure aluminium oxide, also known as alumina. The raw material for this is a reddish-brown rock called bauxite. However, bauxite is full of impurities like iron oxide and silica. Putting impure bauxite into the Héroult electrolytic cell would be inefficient and create a poor-quality metal. The world needed a way to wash the bauxite, to refine it into pure, powdery white alumina on an industrial scale. Without this step, cheap aluminium would remain just a laboratory dream. The solution came from an Austrian chemist named Carl Joseph Bayer. In 1888, just 2 years after Hall and Héroult's discovery, Bayer developed a chemical process to do exactly that. The Bayer process involves crushing the bauxite and mixing it in a hot solution of sodium hydroxide. This dissolves the aluminium-bearing minerals, leaving the impurities behind as a solid red mud. The remaining aluminium-rich liquid is then cooled and seeded with crystals, causing pure aluminium hydroxide to precipitate out. When this is heated in giant kilns, the result is pure white alumina powder, the perfect food for the Hall Héroult cells. With the 1-2 punch of the Bayer process and the Hall Héroult process, the industrial production of aluminium was born. The price of this once precious metal plummeted. In the 1850s, it cost thousands of dollars per kilogram. By the early 20th century, the price had dropped to well under $1. This dramatic price drop opened up a universe of possibilities. Suddenly, engineers, inventors, and designers had a new material to play with. It was strong, yet incredibly light. It didn't rust like iron. And now, it was affordable. The age of aluminium had truly begun, and it was ready to reshape our world in ways no one could have predicted. The first industries to embrace this new wonder metal were diverse. It was used to make high-end cookware because it conducted heat so well. It found its way into decorative items and jewellery, retaining a bit of its luxurious past. But its true destiny lay in more ambitious applications. Electrical engineers realised that, while not as conductive as copper, aluminium was so much lighter that it was perfect for long-distance overhead power transmission lines. You can see this legacy today, strung on towers all across the country. From the kitchen to the power grid, aluminium was rapidly becoming an essential part of the industrial landscape. What makes aluminium so special? It's all about its atomic personality. An atom of aluminium is lightweight. For its weight, it is surprisingly strong, and it has a wonderful chemical trick up its sleeve. When exposed to air, its surface instantly forms a very thin, very tough, invisible layer of aluminium oxide. This layer acts like a suit of armor, protecting the metal underneath from rust and corrosion. This combination of being lightweight, strong, and corrosion-resistant makes it a kind of superhero among metals. And there was one burgeoning industry at the turn of the 20th century that desperately needed a hero like this: aviation. The dream of human flight is as old as our species. But early airplanes were flimsy things made of wood, fabric, and wire. They were fragile and underpowered. The Wright brothers, on their historic first flight in 1903, even used a custom-built, lightweight aluminium crankcase for their engine to save precious weight. They knew that to truly conquer the skies, every single gram mattered. As aircraft design evolved, engineers searched for a material that could provide the strength of steel without its crushing heaviness. They found their answer in aluminium, especially when it was mixed with small amounts of other elements to create even stronger alloys. World War I saw the first widespread use of aluminium in military aircraft, particularly in the frames and engine components of German Zeppelins and airplanes. But it was during World War II that aluminium truly became the metal of air power. The demand for military aircraft like the B-17 Flying Fortress and the P-51 Mustang was enormous. These planes were not made of wood and canvas. They were sleek, powerful machines built with aluminium skins and skeletons. Entire factories were dedicated to producing sheets of aluminium alloy. The war effort required so much of it that citizens were encouraged to donate their old aluminium pots and pans to be melted down and reborn as warplanes. After the war, the jet age dawned, and aluminium was right there to make it happen. The first commercial jetliners, like the de Havilland Comet and the Boeing 707, relied on polished aluminium bodies to slice through the air at incredible speeds. The material strength allowed for pressurized cabins, letting passengers fly in comfort high above the weather. Its lightness made long-haul flights possible and more fuel-efficient. Every time you step onto a modern airplane, you are stepping into a structure that is, for the most part, a testament to the properties of this remarkable metal. It is the element that lifted humanity off the ground and carried us into the sky. Once aluminium conquered the skies, it began to transform the world on the ground. Its unique properties made it the perfect candidate for a revolution in construction. Architects and builders began using it for window frames, door frames, and roofing. Unlike steel, it wouldn't rust, meaning less maintenance and a longer lifespan. Unlike wood, it wouldn't rot or warp. Its lightness made it easier to transport and install, especially in the construction of towering skyscrapers. The gleaming curtain walls of many mid-century modern buildings are a direct result of the availability of affordable, durable, and beautiful anodized aluminium. It literally changed the face of our cities. The revolution continued right into our homes, especially in the kitchen. The aluminium can, introduced in the 1960s, was a game changer for the beverage industry. It was lighter than the steel cans it replaced, which meant lower shipping costs. It was easy to form, easy to open, and, crucially, it didn't alter the taste of the drink inside. And because aluminium chills so quickly, it delivered a refreshingly cold beverage on a hot day. At the same time, aluminium foil became a household staple, an incredibly thin, flexible sheet of metal perfect for cooking and food storage. From the soda can to the foil wrap, aluminium made our lives more convenient. But the ambitions for this metal went far beyond cities and kitchens. They reached for the stars. As humanity prepared to take its first steps into space, engineers at NASA faced the same challenge the Wright brothers had: every gram counts. Sending a kilogram of anything into orbit requires a tremendous amount of energy. The Saturn V rocket, the colossal machine that carried Apollo astronauts to the moon, was a masterpiece of aluminium engineering. Huge sections of its structure and its massive fuel tanks were built from special high-strength aluminium alloys. The metal was strong enough to withstand the violent forces of launch, but light enough to make the journey possible. The Apollo lunar module, the fragile-looking craft that landed on the moon's surface, was also made largely of aluminium alloys, covered in a thin skin of gold and aluminium foil for thermal protection. On the grandest stage of human exploration, when we left our home planet for the first time, we wrapped ourselves in the protective embrace of this versatile metal. From the tallest building on Earth to the spacecraft that ventured to another world, aluminium has been our silent partner in pushing the boundaries of what is possible. It is a symbol of our desire to build higher, travel faster, and reach farther than ever before. One of the most incredible, almost magical properties of aluminium is its capacity for endless renewal. It is 100% recyclable. This means you can take an old aluminium can, melt it down, and make a brand new can with no loss of quality. You can do this over and over and over again, forever. The aluminium atoms in the can you are holding today might have been part of an airplane 50 years ago, or part of the capstone on the Washington Monument over a century ago. This makes aluminium a truly sustainable material, a permanent resource for humanity if we are wise enough to keep using it. This recyclability is not just a neat trick, it is profoundly important for our planet. Remember the whole Héroult process. It requires a huge amount of electricity to break the strong chemical bonds in alumina and free the aluminium metal. Making aluminium from its raw ore is one of the most energy-intensive industrial processes we have. But recycling is a different story. Making a new can from an old one uses only about 5% of the energy needed to make a can from bauxite ore. That is a staggering 95% energy saving. Every can we recycle is a massive deposit in our planet's energy bank account. This is why recycling aluminium is so critical. It reduces the need for mining bauxite, which can be damaging to landscapes. It drastically cuts down on greenhouse gas emissions by saving enormous amounts of electricity. Today, a huge portion of the world's aluminium supply comes from recycled scrap. Major aluminium-producing countries like China, Russia and Canada are also big players in the recycling industry. The journey of an aluminium can from your recycling bin back to the store shelf can take as little as 60 days. It is one of the most efficient and successful recycling stories on Earth, a closed loop of creation and recreation. The story of aluminium is far from over. It is now more important than ever as we look toward a greener, more sustainable future. Electric cars, for example, rely on lightweight aluminium frames to offset the heavy weight of their batteries, increasing their range and efficiency. The next generation of airplanes will use new and advanced aluminium alloys to be even lighter and more fuel efficient. Its journey from a hidden element in ancient clays to a treasure for an emperor to the backbone of the modern world is a mirror of our own journey. The story of aluminium is a story of human curiosity, innovation, and our ever-growing understanding of the cosmos and the elements within it.